All right, so we have nitrogen, assumed to behave as an ideal gas, undergoes a constant pressure from 10 psi, 400 degrees Fahrenheit to 600 degrees Fahrenheit. We want to figure out the change in specific volume and the change in internal energy and the change in enthalpy. And we're going to assume that specific heats are constant. So perfect. So let's go ahead and write down what we know, what we got to find, and what we're going to assume. So our given, oops, let's make that a little bit better here. So our given, we've got nitrogen. We are going to assume some things. So first of all, we're going to assume that it's an ideal gas and constant Cp and Cv. We're going to take it at the average temperature because that is best practice. And we want to find the change in specific volume. We want to find the change in internal energy, and then we also want to find the change in enthalpy. Let's see, constant pressure process. So P1, P2 are equal to one another at 10 psi. And then we have our temperature, oops, which is T1 is 400 degrees Fahrenheit, T2 is 600 degrees Fahrenheit. And so what we're going to do now is we're going to just look at a couple of things that we need. Number one, table A1E. This is going to give us our molar mass for nitrogen. Notice it's in pound mass per pound mole. Then we also have table A20 we're going to need some values out of. These are going to be in BTU per pound mass degree Rankine. We're looking at nitrogen, and we are looking at an average temperature between 400 and 600, which is going to be 500. So our CP value and our CV value. So those are the values that we're going to be needing. All right, but let's go ahead and get back to things. So first of all, I need to find the change in specific volume. So this is going to be V2 minus V1. We're using our ideal gas law. So RT2 over P2. And this is, oops, minus RT1 over P1. This is similar to the previous one because the pressure is constant. So this is going to be R bar over our molar mass, 1 over P, and then delta P, or delta T, sorry. So obviously we got the English units, so we do need to be a little bit careful here. Of course, your specific gas constant, we're going to have to calculate that based off of the universal gas constant. So in English units, we have two values that we can use. We've got 1.986 BTU per pound mass, actually pound mole, sorry, degree Rankine. We've also got 1545 foot pound force per pound mole degree Rankine. So we'll see which one makes sense. All right, so I don't know, I think the 1545, I have a good feeling about that one. But again, there's no wrong answer. It's just maybe one is a few less steps than the other. So I'm going to do 1545 foot pound force per pound mole degree Rankine. Then I've got my molar mass. Let's see. Whoopsies. So my molar mass, 28.01, right there in table A1E. So 28.01 pound mass per pound mole. Looks like already, I'm going to cancel out there, times 1 over my pressure, which is 14, sorry, not 14.7, 10 psi, which is pound force per inch squared. Perfect. Looks like already I've got a pound force and a pound force. And then my delta T is going to be a change between 400 and 600. Now, yes, right? Delta T, I could say 600 degrees Fahrenheit minus, oh, I'm going to sneeze. Maybe not. 400 degrees Fahrenheit. And this is going to be 200 degrees Fahrenheit. But you could also, go ahead and put it in Rankine. So this is 600 degrees Fahrenheit plus 460. That would give you degrees Rankine, minus 400 degrees Fahrenheit plus 460. That would be degrees Rankine. And it would give you the same thing. It's a change in temperature of 200 degrees Rankine. So again, this is the change. And we've said that before. Oops, actually, this is what I want. We've talked about that before, how the change in temperature is the same in degrees Rankine as it is in degrees Fahrenheit. The change in temperature, if you're in SI units, are the same in degrees Celsius as it is in Kelvin. Okay. All right. So let's go ahead and put that on there. So I can write 200 degrees Rankine or 200 degrees Fahrenheit. It really doesn't matter. You can see those guys cancel out. All right, so it looks like, well, I need units of, say, well, it's volume per unit mass. So the units of volume have got to work out. I'm going to say, let's put it in feet cubed per pound mass. So I've got an inches, so 12 inches squared is equal to 1 foot squared. And I think that should work out. So I've got the inches squared, and then all I should be left with, I've got the feet squared over pound mass. So let's go ahead and calculate. So it looks like 7.7. I get 7.66, but we'll go ahead and 7.66 feet cubed per pound mass. So that's the answer for that guy. All right, so that's part B. And then I need to find the change in internal energy. And because I have an ideal gas with constant specific heats, so I'm making both of those assumptions, delta U can be approximated as CV delta T. All right, my delta T, remember, is the 200 degrees Rankine. Okay, my CV, let's see what I'm going to use. I'm going to use 0.183. So 0.183. The units were BTU per pound mass degree Rankine. And then I've got my delta T, which is 200 degrees Rankine. I could go ahead and write the equation for delta H, which is CP delta T. So let's see, CP, what was he? 0.254. So 0.254 BTU per pound mass degree Rankine, with a change in temperature of 200 degrees Rankine. All right, so that gives us, it's going to give us 36.6 BTU per pound mass for our delta U. And then that's going to give us 50.8 BTU per pound mass. Perfect. All right. Well, thank you for watching. Let me know if you have any questions.